So in section 4.6, we're going to talk about some real routing protocols that are used in the internet. We're going to look at these three specifically and give an overview of them. Recall, as we talked about last time, there are two kind of classes of routing protocols. Routing protocols that we use inside an autonomous system and routing protocols we use outside or between autonomous systems, among autonomous systems. So intra, also called interior gateway protocols, are the kinds of protocols that an organization would run with the routers in its own organization, within that organization. These are three intra-AS routing protocols. RIP, which is this kind of the granddaddy of routing protocols. It was the one that was originally used in the internet. OSPF, and this enhanced IGRP, which is a proprietary protocol from Cisco.
You want to know the acronyms for each, like what each word stands for?
No, I just really want you to know that those acronyms are routing protocols, okay, and that they are intra-AS.
So I don't have to be able to tell you what
No.
OSPF stands for.
No. But it's sort of nice. If that helps you remember it, then that's cool. It's open, which means it's a open standard and anybody can implement it. Whereas that EIGRP, that's a Cisco only thing, and they don't tell people the definition of that protocol. They want you to pay for it, right? But they would say it's better, I'm sure. So this is kind of our big picture view. So we've got these three areas. Within those, there's an internal router, and each of these internal routers are talking to each other via the internal gateway protocols, the intra-routing protocols. So this organization could run RIP, this organization could run OSPF, and Area 1 could run the other one, right, EIGRP. Okay, but the routing protocols that are running on routers that are exterior to them, they all have to be running the same routing protocol, and that's going to be BGP, the Border Gateway Protocol. And that's the one that all exterior gateway protocols have to run that if they're going to be on the global internet. Okay. So first, let's look at RIP and kind of how it works. This was included in the BSD Unix distribution in 1982. So you could run RIP if you were running Unix, and you could run your computer as a router. So it's a really old and open routing protocol. It's a distance vector algorithm, so that means that we have to send our distance vectors to our neighbors. You remember that? So it's the reachability information of all of the nodes in the network, but I just have to send it to my neighbors and exchange that. The distance metric that it uses, so the numbers that are stored in that vector, represent the number of hops, which those hops are the number of subnets traversed. So it's how many subnets you go through is what the count would be. And it has a limit of 15 hops is the maximum you can fit in there. So that means they probably used a 4-bit field to represent that. So that means what happens if you have a network over which it's wider than 15 hops, that means you don't use RIP in that network. That would be like a lot of subnets, but certainly the real internet, the current real internet right now, is too big for this to work. But that's why this is just used as a intra-AS. Certainly at Freed, our network's not more than 15 subnets across. This table kind of shows you an example of how that math would be done. So if you're router A and you're routing to a destination that's in U, that's one hop because there is one subnet, the subnet that U is in. Yeah. If we're going from router A to a destination in Y, that's 3. So that's 1, 2, 3. These subnets don't have names, but they're different subnets between routers. You with me? Okay, so that's what that is. The way RIP works is it sends out advertisements, and these advertisements are the distance vectors. Remember how we said that you exchange distance vectors among your neighbors. RIP sends out distance vectors every 30 seconds, and sends out a response. This advertisement can list up to 25 destination subnets within the autonomous system. So that means that this distance vector could be up to 25 things long. The book goes through this example of how a router A, might receive distance vector information and update its forwarding table based on that information. So when it receives an advertisement, you can see this is kind of like the distance vector here. This is to destination W, and we receive this. We receive an advertisement from A to D. So D is receiving this, and it's updating its data, its routes. When it finds a lower cost route, then it'll replace it using the Bellman-Ford equation. Remember that whole minimum of the cost, the least cost path plus the cost to get to that node. It's important to be able to know if a link goes down. So the way that RIP defines this is if you don't get an advertisement in 180 seconds, so that would be in 6 rounds, right? Because they should get it every 30 seconds. If you miss it, if you're down for 6, then it assumes that you're dead. It'll put an infinity as your value. No, it'll invalidate all of the routes from that neighbor. So if the neighbor's down, we do not trust him. We're not going to send any data to him. And it'll send new advertisements to its neighbors saying, I've discovered that this guy is down. Okay. The routing tables themselves are managed by a program called Route D. And it's an application level process, a daemon, like a background process that's running. These advertisements are sent in UDP packets, and they're periodically repeated. So RIP is implemented over a UDP, which might seem a little bit weird, but it's not that weird. In that, it's a network layer kind of protocol, but it uses UDP, which is just basically this very thin layer on top of IP. Okay. Let's talk about OSPF. OSPF is an alternative to RIP. I think it's quite a bit newer. You can check out RFC 2328 if you want to see all the details, all the dirty details of how this works. It's a lot more advanced, has a lot more features. It is publicly available. It's open, so it's just a matter of you implementing it. You don't have to pay anybody to see the specs on this. It's a link state algorithm. Remember link state? That means I have global knowledge. I know all the costs of all the links in the network, and I'm going to get those by sending messages across the whole network. I'm going to flood the network, right? I'm going to have global knowledge, so that requires global communication. And then we're going to use Dijkstra's algorithm to, once we have the complete topology information, to find all the least cost paths. It uses advertisements as well, where an advertisement carries 1 entry per neighbor router, and it's disseminated. The advertisements are disseminated through flooding within the autonomous system. So, so that makes sense, right? If we're an autonomous system, we kind of know there's kind of a bound on how big that thing can be, and in that case, flooding is acceptable. Now, we might not want to flood the entire internet, the global internet, with packets, but we can accept it with this. It's really, really complex. The whole protocol is, and I'll show you the advanced features next. And you can just imagine when you see all these features that look really nice to have, there's got to be a lot of complexity built in to allow those. And we'll say, unlike RIP, OSPF messages are sent directly in IP. So it doesn't encapsulate it in a TCP segment or a UDP segment. It's just straight IP datagrams. These are some of the features that OSPF offers. It offers security. All OSPF messages are authenticated. So this will make sure that there isn't a malicious intrusion, malicious propagation of information. It also supports multiple same cost paths. In RIP, you can only have one path that's allowed. So if there are two ties, RIP will always choose one, I believe. You could also use multiple cost metrics. You remember the cost metric in RIP? It was always the number of subnets. That's the cost for each link. With OSPF, you can use things like, you can have different types of service for different things. You could have, the link costs are configured by the network administrator. They could be the shortest path, or they could be related to bandwidth or other things. So OSPF gives you more control as to saying, how is it that I want to choose routes? Is it just the number of subnets, or am I going to consider other factors? RIP doesn't even give you that option. It supports multicast. Multicast is a way of sending one message to multiple recipients, kind of sending to a group, and OSPF supports that. And there's also a hierarchical version of OSPF. If you have really large domains and you want to break your domain into groups like this, you can do this. If you have a two-level hierarchy, you can just barely see the color on this board, but the backbone routers up here are one level, and then each of these little areas underneath there are another level. And within that, you only have to send out the link state advertisements in the area. So each local area will flood that area to exchange information, and the backbone will flood the backbone, so they all know how to get to each other. But this backbone router up here doesn't have to hear this guy's flood at the bottom. So we're only finding the least cost within those areas, but they're hierarchically structured, so we can get anywhere we need to go. And he defines here how we have kind of three different roles for routers. We have the boundary router, which is connecting to the exterior internet. We have the backbone routers up here, and then we have the area border routers. So they're kind of serving like a boundary router, but for that area. You see what this is just a hierarchy in OSPF. You can't do this in RIP. Okay, the last thing we want to talk about is BGP, and BGP stands for the Border Gateway Protocol. This is the inter-AS routing protocol. Right? This is the protocol that has to be run to connect multiple autonomous systems to each other. It is the de facto standard this is the protocol you have to use because everybody else uses it, and everybody has to run the same one. It allows autonomous systems to obtain reachability information for other subnets. It allows autonomous systems to share that reachability information to internal routers as well. And it allows you to determine good routes to external subnets based on reachability and based on policy. So this is what we said before, that when we're dealing with multiple autonomous systems that are routing to each other, there may be the case that since large organizations, corporations, or countries are involved, policy decisions may be more important than what's the shortest route. All right? And I think we're going to talk a little bit more about that in just a second. BGP is really complicated. It makes sense that it would be really complicated because it has to do everything. They define different roles. There are BGP peers, which are pairs of routers, and there are BGP sessions between peers. These happen over semi-permanent TCP connections. It's one of my favorite words in the book, semi-permanent, sort of like semi-pregnant. I don't know, like some things you just are or you're not, right?
Bad example.
Was that a bad example?
That is funny.
All right. You can have external sessions, and that's when you have a BGP session between two routers in different autonomous systems that are exchanging information. And you can have internal sessions between two routers within the same autonomous system. You see, since BGP kind of has to be the glue, right? It has to allow different autonomous systems to talk to each other, but in order for that to work, every router in your network has to know about how to get to external routes. For example, imagine you're 1D here. If you're 1D and you need to send packets to an external autonomous system, you can't just send it to one node and be the shortest path, right? It depends. If you need to send it to this autonomous system, you probably need to go through 1C. But if you need to send it to AS2, you probably need to go through 1B. So those routing, like that's another routing decision that has to be known. Note in this case, the destinations. So when we're talking about the information that's being exchanged, we're not talking about destination addresses. We're not talking about individual hosts anymore, but we're really talking about prefixes, where those prefixes encapsulate a network, a whole subnet, or maybe even a group of subnets. So destinations are prefixes, which represent networks. They're not hosts anymore. We're at a higher level than that. He gives this example. Suppose we have this exterior BGP session between 3A and 1C. Okay, so those two guys are talking to each other. AS3 is going to send the prefix reachability info to AS1. Then 1C can use an internal BGP session to distribute the new prefix information to all the routers in AS1. So yeah, right. So he's kind of he's the gatekeeper. He's on the outside, and once he gains new information to say, hey, if you're going to route to anything if you're going to route to 3A, or really maybe if we're thinking about prefixes, if you're going to route to a 3, you need to send through me. But it's got to tell all the other routers that. In this case, then 1B could re-advertise its reachability information to AS2 over this 1B to 2A connection. So if the routers in AS2 need to route to AS3, they're going to have to go through AS1, yeah? And hopefully the policy is set up to allow that, since that's the only way to get there in this example. A route is really composed of a prefix and some attributes. So we've got a prefix, which represents a network, and we've got some attributes about that. And there's lots of attributes. Two important ones are the AS path and the next hop. The AS path contains the autonomous systems through which the prefix advertisement has passed. So if we've got, this is sort of like the path of autonomous systems that you have to go through to get to this prefix. So if it were a shorter number of paths, a shorter number of autonomous systems, then that would probably be a faster path. However, right, because you've got that information, if you have policy decisions that you're not going to route anything through AS49 because you hate him, right, you can see that there's a 49 in that AS path, and you will not use that route. Okay. Next hop indicates the specific internal autonomous system router that's the next hop. There's an import policy. When a gateway router receives route advertisements, so that's when an external router receives advertisements, it has a policy about whether to accept or decline this route. And that's based on policy, right? RIP, we would always accept information coming from people because we trust the host in that network. Or in the case of OSPF, all those hosts have to authenticate, but if they're authenticated host, we're going to listen to their information. We're going to take their routes under consideration and find the shortest path, or the least cost path. In this case, we're saying we may get routes which sound awesome and which are awesome, and we're going to throw them out because AT&T is not going to send anything over Verizon's network because they haven't paid Verizon to do that. They've paid somebody else, and that's who they can send their traffic over. These are some of the route selection rules. There are these elimination rules. Basically, the router can learn about other routes, but it's going to go through this set of rules to eliminate routes that it won't choose. So it's kind of, this is a priority preference order. We're going to first follow the policies, right? Always follow the policies first. After the policies, we can find the shortest AS path. Remember this, so if one route takes 3 autonomous systems to get through, to get to that network, and the other one takes 1, right? Well, the one autonomous system is shorter. If it's a tie, if it's the same number of autonomous systems in the AS path, then we can look at the next top router and choose the one that's closest. Or we might have additional criteria as well, that besides these 3. BGP messages, so all the information we have to exchange in these BGP sessions, either internal or external, is exchanged over TCP. This is an example of some of the messages that exist. So if we want to open a connection, we're going to send the special open packet. If we want to update to advertise new routes or delete old ones, we can do that. You see, we can send keep alive packets. We can also send notifications. Notice this. Imagine here, this is beginning to get more in the real world where, right, network connections are, bandwidth isn't just given away, right? Somebody's always paying somebody else for this connection because somewhere up the chain, somebody has paid a lot of money to own this network and all those resources. So if we've got kind of 3 big dogs here, the 3 network providers A, B, and C. X, W, and Y are customers of A, B, and C. X is dual homed, and that means that it's attached to 2 networks. So if
So are they getting services from A and B?
Right.
Or B and C?
B and C. And maybe I guess that would mean, though, they're probably well, let's move on. This in this scenario here, A is going to advertise this path AW to B. So if B needs to get to W, it can go through A. B is going to advertise the path BAW to X. So if X needs to get to W, it can send it through BA. And then the author asked this question, should B advertise BAW to C? And the answer is no. And why is the answer no?
Because it can get through, it can get to W without needing to use B, so we waste some B's bandwidth.
Exactly. B does not want to provide service for C when C can get to it through A. So any routes that can be gotten to through other means, we'd prefer that because then B's kind of wasting its bandwidth on that. B wants to force C to route through A as much as it can to just offload that work. All right, so to sum this up, why, and this would be an excellent test question, why are there different protocols for doing intra and inter-AS routing? And it's kind of something we talked about last time. Remember the Pinocchio thing? One thing is policy. That keeps coming up in this discussion, right? Policy. We want to enforce different policies in different levels of our networks. And intra-AS has a single network administrator, so policy is easy to implement because he's in control of the whole system. However, with inter-AS routing protocols, the administrator is going to want control over how his traffic is routed and who routes traffic through him. So that's one of the differences between the 2 types of routing, intra and inter. Policy. We want to be able to support policy in inter-AS routing. Scale was kind of one of our starting points. We need to use hierarchical routing in order to reduce the amount of updates we have to send to everybody, right? It kind of breaks, it's kind of a divide and conquer thing, right? It's just the network of networks, which is the internet, is too big for it to all be one network that's flat. We need to break it into parts where there are kind of backbone networks that connect networks to networks, which is autonomous systems. This also saves the table size, right? So really, in the end, when you're talking about how big is a forwarding table, there's only so many different routing decisions that can be made because you can only kind of see as big as your system. And lastly, performance. Right, performance is always key. It's always important. With an intra-AS routing protocol, performance is really important. Right, you want our interior, organizational routing to be as fast as possible. But that's not necessarily the case with inter-AS routing. When we're routing between autonomous systems, what may be more important than performance? It's a word that's on the screen. Policy. Right? So it's not just about how fast can I do this, but has this organization paid me money to route for them? Because I'm not going to do that if they don't pay me. Okay, so that's 4.6, how we do routing in the real internet. We looked at BGP, we looked at OSPF, and RIP, which are just 3 of many routing protocols, but 3 pretty common ones.
Trying to understand